Okay, so what we were looking at last time was that we had n players. We had n players, and each one of them had a row of adjacency matrix. Okay, they had a row of an adjacency matrix. Okay, each contains. Here's a central player C. Their goal was to communicate a message to C such that looking at C, such that looking at messages, C can decide whether G is connected or not. Right? So one way was that they could just pass their row itself to the central player. Now central player has basically adjacency matrix. Now he can run any algorithm here and check whether this is connected or not, right? But our goal was that it sends as few messages, like as small messages as possible, and we showed last time that there exist messages of size n polylog in bits, like polylog in bits messages exist, such that so total amount of messages that will be sent to C is like n polylog n, and do this. So to do this, and we also assume that there is a public randomness. Okay, so what do you mean by public randomness? Okay, so everybody has the same random source. So like A has something with the same set of matrices. Okay, and we motivated everything, and the one lemma which was crucial, and this is a lemma which we will be using it at least for next 3-4 lectures. So let's look at it more carefully. And what it says, this lemma says, is that here's the lemma. There exists a random matrix A, okay, A of dimension, okay, A in say R big O of log square n times n, okay. So this is a matrix with small number of rows, but the number of columns are large, okay, such that for any x in R to the power n, okay, for any x in R to the power n with probability at least at least 1 minus 1 over n to the power c, and this n to the power c you can make as large as possible, we will see. We can learn ixi, okay, ixi for some xi, okay, not equal to 0 from ax, okay. So what does it tells us? Okay, it tells us that there exists a random matrix A, okay. So it is important to have a quantifier correct here, okay. So we have a random matrix A, okay. Now what does it tells us? That look, if you give me a long vector x of dimension say n cross 1, yeah, n cross 1, then what does this tells us? That look, there are some entries which are non-zero here. I don't know which entries are non-zero, but if this matrix has a property that if you multiply with Ax, you get some vector of dimension how much? You will get a matrix, a vector of dimension log square n times 1, right? So I'm just forgetting for a moment big O of, so some alpha times log square n. And what does it tells us? That look, looking at this small vector, I can find a non-zero entry here and its index, value and the index. This is what it says. In fact, the way we will use when we will finally use it in a numerical algebraic methods, we will be actually able to show that it returns one of these entries like non-zero entry with uniform probability. So it's like it returns an index from its support with uniform probability. Okay. Okay. So this was our main lemma. And how did we made this lemma? So we said, okay, fair enough. And to prove this lemma, we introduced this method of what I call geometric sampling. Okay. So what was the geometric sampling idea? And it is important that we understand the idea of geometric sampling. So to prove this, we introduced this idea of geometric sampling, and what we said, okay, let's make this matrix A. So for now, we are going to make this matrix which is like log n times n. Okay. So what was this matrix? Some 3 log n times n. So first, we constructed a matrix which had the following property. Okay. Let's call this matrix A1. What was A1? In the ith row, I put, so I start from 0, 1, 2, okay. Ith row, I put 1 with probability 1 over 2 power I. Okay. So if you notice, first row is probability 1, everywhere it is 1. Because I put 1 in the 0th row, I put 1 with probability 1 over 2 power 0, which is 1. Right? So what do I do? So you can think of this, how do I construct a row of this A1? Is like I go to each entry, toss a coin with bias or with pi 1 over 2 power I, and if it comes head, I put 1, I put 0 otherwise. Okay? So this is what our matrix was, A1 matrix. Now notice what does A1 tells us? A1 is trying to capture, like, look at your x, like look at your x, right? So it is trying to capture, if you like, in certain sense it is trying to capture from this x subvectors of x, right, such that at least one of the subvectors is a sparse, right, and then we can do a sparse recovery, right. So you can think of this one, it picks up everybody, right, but so this row is useful for whom? It is useful for those x's where there are very small number of ones or a small number of non-zero entry, then this guy will be able to pick those guys up. But if it has too much of ones and I want a sparse subset, then if I multiply, because as you go down in this matrix, the number of non-zero entries here drops exponentially, it drops by half. Because what is the probability that number of ones, what is the expected number of non-zero entry in the second row? Is half. Because each entry is 1 with probability half. So n by 2. Second, n by 4, n by 8. And as we go down, the number of ones in these rows drops like by half. Okay. So basically it is about what is the right row which captures the sparsity from here, and given that sparsity, we will be able to recover correctly. So basically there is a notion of sparse recovery which I am just hiding it away for now, but it is basically based on that fact. Okay. Okay. So this is what we made this matrix. Okay. So notice, if it is 0, 1, whatever it is going to get, it is going to give me a value of this x, right. So now we said, okay, fine, but this will never give you the index. Okay. So then we made another matrix which we called A2. And what was A2? A2 was basically I went to A1 and I wrote down the column entries, right. So for example 1, 1, 1, 1, 1, so I would write 1, 2, 3, dot, dot, n. So if I go and 1 again, if it is here, I will put 3. If it is 5 here, 5th place I have 1, then I will put 5. Here it is some n by 2, then I will put n by 2, so on and so forth. So I replace, so what is it? Replace 1 in A1 with the column entry, with the column index. This is what we do. Okay. And then we took the third matrix, and that was just to take care of the fact that, you know, look, so if all would have been done well, great, excellent, and what would have happened is that, imagine yourself that there exists some row, like there exists some I such that let's call this, each row I'm going to call S0, S1, S log n. Okay. If there exists I such that Si, look at Si, right? So it gives you, I can think of Si as basically index where it is 1, okay? So SIB, let those indexes, column indexes in AI, okay, that are non-zero. Okay, suppose I can find such an Si. This is the definition of Si, such that now look at the non-zero entry of X. Let I be row number, or I be j such that Xj is not equal to 0. These are those indexes for which this is non-zero. So I have just collected the indexes for which it is non-zero. So if Si intersection I is a 1, if somehow I can prove that Si intersection I is, there exists some Si for which it is 1, then it is very easy to infer what this is, because when I look at this and I look at this, what do I get here? Like suppose this Si intersection I is 1, and in fact Si intersection I is some j. Then what is this sum and this sum going to give you? This sum is going to give you, like if you look at this row and this row, this is going to give you Xj. But what is this going to give you? This is going to give you j times Xj, right? Because in the same place, what I have kept? I have kept the column indexes. So I'm going to get j times Sj. So if this property would have been true, then j times Xj, so this is what I call A last time, and this is what I call B. So if I divide A by B, then what I get? If I divide A by B, okay, then I get like the index. And what is B? Is the value. So this is what it was. Okay, but this was not enough for us to prove. Then what did we introduce? We introduced another matrix A3, right? A3. And what was the property of A3? We chose a random number R in 1 to some poly n, poly capital N, and we choose R in this randomly, uniformly at random. Okay, and then what they do? We look at A2, okay, and we replace in A2 with the integer A with R power A. So basically it is R to the power column number. This is what we did. So our matrix A was basically consisting of A1, we made A2, then we made block A1, and then we made block A3. This is what our big matrix was, okay? And what was the size of this matrix? 3 times log n times r. And what did we prove about this matrix? We proved certain interesting properties about this matrix, okay? So what were the properties we proved about this property, and what was our test? Our test was, okay, we said, look, this is good, great for me, right? But the test which we applied last time, we said, if for some s in s0 dot s log n, following happens. What was that? What did we define? A was summation. You can think of this, these are indexes, right? So this is basically, I can think of this A equal to j in S, where is A? A will be from here, okay. So what is this? J in F, j times Xj, right? What is B? B is summation over j in S Xj. And what is C? C is going to be, so think of this, this is why I wrote A1 first. Look at the corresponding, like for some S, so I have fixed F, means I have fixed the row here, row here, row here. Okay, and what will be C? C will be again j in S r to the power j xj. Okay, and we said that S passes a test. What did we say? S passes a test if first A by B is in 1 to n, that was the first thing. And secondly, what did we say? Okay, now I know that A by B gives me a column number, right? So what did we say? Second, R to the power A by B, right? R to the power A by B is equal to, or what am I writing? Okay, so I have C here, right? So C equal to B times, which is xj, times R to the power A by B. If this happens, okay, and this will happen, we will do mod P. We choose R between 1 to blah blah blah, poly n, where P is some prime, some 1 to P where P is like some poly n. Okay, so these are the tests which I do. What do? I did my test. What is my test? I said, hey, is A and B in n? Like, is this a correct index? Fine. Oh, if this is a correct index, then I know that whatever the C gives me should be equal to B times R to the power A by B, R to the power column index, right? Why? Because what is my hope? My hope is that I have just extracted one element using all this process. And then what did we show? We showed something interesting after this. So this is a lemma we showed. I'm not going to give you a proof again. If I intersection S equal to 0, is equal to n, 1, then S passes the test with probability 1. Then S passes the test with probability 1. Secondly, if I intersection S is not equal to 1, then S does not pass this test with high probability. Okay, then S does not pass this test with high probability. Why? We said, look, if I intersection S is more than 1, let's consider I can think of this R being not substituting something, but R being an variable. Then what does this tell us? Then it tells, suppose Z. So we say, oh, if Z is equal to, what is this? J in S, xj, z to the power j, right, minus b z a by b, right, mod p. Okay, so when will my test fail? When this equality holds, right? My test is going to fail. Okay, I passed first guy, fine, this is some index, but I can still fail because, well, I wrongly told you, like you also wrongly passed this test. But what is the probability that you will wrongly pass this test? It means you must be root of one of these guys, right? But what is the degree here? Degree of f of z is equal to n. So if I choose huge number of polynomials, like huge large size p, like poly n, then the probability that I will fail is like 1 minus 1 by poly n, because there are only n roots, right? So if I choose something which is not a root, you will not fail this test, right? And this is not something which is very clever or something. This is how you do distinguishing between one and more. This is a standard trick applied in like most places. Okay. Okay. So this is what we prove first, right? So this is why we introduce third thing. So for example, if I have asked you, forget about all this. If I had just asked you, if I told you that this guy is one sparse, like it is exactly equal to one, right? Then it is enough that you keep this row and you keep this row, and then you will be able to get the value. But if I just asked you that is it more than one, then the only way to do is to choose an R big enough and do this. Okay. So even to distinguish between one and more, you need this test. Okay. Okay. So this is the lemma we proved, and this is the proof. I mean, this first one is easy. Second, it is because of this. And but most importantly, what we proved is that another lemma which we proved last time. Okay. There exists some S in 1 to S in S0 S log n such that S cardinality or probability that I intersection S is 1 is greater than or equal to some 1 over constant. Right? So what does this tells us? Okay. If we apply this test, what is the probability that we will actually get the correct index? It is, look, I need to pass all this test, right? I need to, so what is the probability of failure? Probability that I will fail here is with some constant probability. So this whole process, like other things are, I pass with very high probability, but I can fail because I can fail for two reasons. I can fail because my test failed, but test fails with very small probability. I can also fail because there is no S here whose intersection with my index set is 1. Then also I can fail. But that happens with probability at most 7 over 8. That happens with probability at most 7 over 8. So with constant probability, I will success, right? So what should I do to boost my probability to anything? I will rather, I take A1, A2, A3, right? And I repeat this A1, A2, A3. In the sense, I construct another A1 prime randomly, then A2 prime will be constructed randomly, then A3 prime will be constructed randomly. What is the probability that will fail with the first guy and fail with the second guy, right? 1 minus 1 by 8 times 1 minus 1 by 8. Okay, fine, great. So if I repeat this log n times, what is the probability that I will fail? I will fail is like constant 1 by e to the power log n. So with probability 1 minus 1 by log to the power n, I will succeed. And this is, if you look at the theorem, you have log square n, right? Because one matrix gives you log n, and that will only boost my success probability to a constant. So to boost my success probability, I do things in like parallel. Okay. So this is why you get order log square n times n. And you can choose any constant you like, 1000, 10,000, 5,000, and you can make this as small as you like. Right? You just have to also choose here the same thing because, okay. So this is what we did last time. Okay. Now there are two questions, right? So now we will make it work for sketching, okay? But let's just keep this lemma in mind and let's try to do whatever we did. So this was one ingredient of our algorithm. The second ingredient of our algorithm was what is called Okay. So what we used is what is called Borovka's algorithm. Okay. So what is Borovka's algorithm? For each node, select an edge. Select an edge, select an incident edge. And second, for each connected component, select an incident edge. And when it says incident, with one endpoint here and other endpoint. Repeat above line until process terminates. Okay. Now, what did we prove last time? First of all, we proved that this will terminate in log n round. This is what we proved. Okay. And the set of all edges that we have selected, set of all edges selected contains a spanning forest. Right? Contains a spanning forest of the graph. So if I have kept enough, I have kept this set of edges, looking at this set of edges, I can make my spanning forest and I can tell you whether the graph is connected or not. In fact, I can tell you the number of connected components of my graph. Right? Now, we wanted to do this using this. Right? And to do this, we would like to do what? We would like to sketch the neighborhood, or my neighborhood, and give it to the central player. And to do that sketching, one normal way would have been to sketch my incidence itself, but it has its own demerits when it comes to adding or subtracting and things like this. Okay. So what did we do? If you recall correctly, so the last ingredient which we used, this was the third ingredient. So this is second, this is the first. There's a reason why I'm repeating it, because this is the backbone of almost all the algorithm which we will see. Okay, so the final thing which we saw last time was what is called find vertex edge, find vertex edge vectors. Okay, now every vertex has name. Say you arbitrarily put them 1, 2, 3, n. Okay, now for each I have a vector. And a vector has a coordinate fixed. It tells me which edge I'm talking about. What is the first edge? One lexicographically 1, 2, 1, 3, 1, 4, dot dot dot. Then it will start 2, 3, dot dot dot, n minus 1, n. Okay. So what is the size of this vector? N choose 2. Okay. And because I know how they are this, if I told you, oh, 10th index there is a 1. What will it meaning of this? The meaning of this will be edge between which I and which j. If I told you that here is a non-zero entry, then I can tell you which I and which j has an edge between them. Okay, and how did we fill this? Oh, the filling was very easy. Look at any edge. Okay, if it is, so I'm going to call look neighbors which are behind and which are neighbors which are forward him. For his behind neighbors, I'm going to put -1. For his forward neighbors, I'm going to put +1. Okay, so behind neighbors -1, forward neighbors +1, right? And 0. So this is a very sparse vector. It has at most n-1 non-zero entries, right? And but what is the property of this? The property which is very crucial for us, which we used last time, was this lemma. Okay, non-zero entries of summation. Let's call this vectors ai. Okay, I in S ai correspond to edge between S and V minus S, right? Because you look at your S and look at V minus S. If there is an edge, one of these guys, and I am summing these vectors, right? So notice first of all, for any I comma j, either he is in ith vector or in the jth vector, and at one place it occurs as positive, other place it occurs as negative, because either I is ahead or j is ahead, right? So if I have any edge here and if I sum the vectors, their corresponding contribution is going to be 0. Look at a vector which is here completely. That guy doesn't even appear here. So this guy is 0, this guy is 0. So this contribution is 0. Only people which is going to contribute 1 or minus 1 is the edges which are going to cross, right? So if I look at the support of these edges, I know that all those guys are edges which are corresponding to the cut edges, okay? And look, by looking at them, I can actually, if I knew this vector, I can actually tell you, this is an edge from 5 to 7, 8 to 9. I can tell you, right? Well, you don't have, you give me a vector, I will read out, oh, you're a 10th guy, means if I have n, if I know the number of vertices, I know what is my order it is. I can just read out. And it is important that we know all these things, okay? If we are going to make a streaming algorithm, we need to know all this thing. All good? Okay. Okay, excellent. But now here comes the algorithm. So it looks natural, right? That what should the player be sending? Player has unbounded properties. So here are your players, player 1, player 2, player n. He has his row, right? He can convert his row into this kind of vector. Let's call it A, like, so this is say some pi, okay? And what did I tell you? They have, so it constructs AI, okay? And here is that random matrix A which is available to everybody, right? This is what, so we are in the case where we have a public randomness, so A is available to everybody, which is a random matrix. What does Pi does? He applies A to it, right? He applies A to it, and let's call it AI tilde and passes to central player, right? So what does central player receives? It receives A1 tilde, A2 tilde, dot dot dot, AN tilde. This is what he receives, okay? How many bits of information I have passed? Polylog n bit. Because each AI has a polylog in size. N is n choose 2. So log square n choose 2, right? I have multiplied what I'm AX I'm sending you, right? I'm sending you AAI. So what is the dimension of this? Is log square n, some order logs. So this is what I have sent you. So total amount of message which I have passed you is in this algorithm up until now. Let's be precise, because then is up to constant I have passed is n square n log, except constants. This is what I have passed the message. Huh?
We also need to bound the entries in the AI tilde, which is okay because P was of order n power c. So this is number of entries, but one entry in
plus 1. No, not plus 1.
not plus one. That randomness would come and
When you multiply, you get a different value.
Log n words. It's words. Okay, if you don't want bits, say words. Right? It doesn't matter. Fine. Okay. Okay. But that is not what. So now I would like to emulate my Woodworkers algorithm using this. Right? What does the first guide tells us? Okay, fine. Let me use my A1 tilde. What will it give me? It will give me an index of AI and its value. Right? It will return me a non-zero entry, either 1 or minus 1 and its index. Then I know an edge. Okay, I make this. Okay, so round 1 is great. round 1, use AIs to get an edge. Right? So now using this edge, what the central player does? Now it gets connected components, connected components, connected components. Okay? Now what does he wants in the second round? He wants to output an edge which is incident to these components. Right? What will he do? Look, suppose here you have A3, A5, A7, A8, like, okay, let's not write them A3, this is not what it is. So let's write them the vertex numbers, okay? So what are the vertex number here? Suppose I have 3, 5, 7, 9, 11. Like this formed a connected component, and now I can see them, right? So what I have A3 tilde, I have A5 tilde, I have A7 tilde, I have A9 tilde, I have A11 tilde. Now what does it tell us? Oh, if you gave me A3 plus A5 plus A7, A9 and A11, then if I looked at the non-zero entries, then those non-zero entries will correspond precisely to the edges which are leaving him, right? Because of my lemma. Okay, but is it true? But now I don't have this, I have just this, right? But now let's apply A to this, right? A applied to this is equal to A, A3, A, A5, A, A7, A, A9, A11, A, A11. Why? Because A is my linear, A is linear. So A of this is A of this. Great. But this I know, I have. This is precisely A3 tilde, A5 tilde, A7 tilde, A9 tilde, A11 tilde. Right? So I sum these guys because I have these things, and I looked at this vector, and I would like to use this to extract an edge incident to this. Okay? This is not going to work. Principle is correct, but it is not going to work. Okay, so let's try to read this lemma.
How do we know that A3 tilde plus A5 tilde dot 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 plus A11 tilde and A3 plus A5 plus A7 plus A9 A7 plus A11, both of this, this is gotten after you applied A to it. So how do we know both of them, when you sum it up, would give us some information about the edges going outside? I mean, if the upper one does, why should the tilde also give me that information?
Yeah, so what is an issue? Like, yeah, I mean, sure, I told just now, so yes, fine, but why? It is more important to understand that why this doesn't give us information. Right? I mean, naively, I would apply exactly this. Keep doing this, right? Because of linearity, I read this. Yeah, why not? Look, imagine yourself, I have not applied this thing, and I have these vectors, I sum this up, okay, and I apply A to that, right? Why will that not give me this information? Suppose here I would have written some different A. Will it give me information? No, I'm just saying, what is an issue? Do you understand the issue? I cannot use the same A. Why? Let's just read it. There exists a random matrix so that for any x, something happens with the probability, right? And what did we apply here? In the first round, we used the same A, right? And the only thing we applied that, oh, any one of them will fail is like n times, so 1 over nc times n, so I applied union bound to bound the error probability in the round 1. But in the round 2, why I cannot use the same A? Why should it not give me an information? Think about it, right? It says, right, for any, there exists a random matrix A, so A I was chosen is random, and for any X in Rn, this should give me this information. So, that X which you had in your head, right, which is A3 plus A5, this is your, say, this is called A star, this is called A star, right? If I would have applied A star to A, what will I get? I will get some of these things only, right? Because of linearity of this. So why should this not give me an information? It should give me information, no? So it doesn't give you information, there should be reason behind it. Like, where are we going? Where are we making a mistake?
Lemma says we can get I comma xi for some I. That may not be the same for when we add it up.
So something should go wrong, no? What has gone wrong?
When you fix A, that study might give us some different values of A3 to A11 in such a way so that this.
What do you mean by A3? What is adversary here? Look, let's read this. It's not a deterministic algorithm, right? It fails. Fails at some set of, look at this, it fails on some set of vectors. Okay, so there are lots of vectors, but there are some set of vectors. However small it is, it does fail. Right? It does fail. Okay. Now, I have already used A for A3 tilde, A5 tilde, A7 tilde, A9 tilde, A11 tilde for this particular A. Now, whatever I have got is determining S. So, with respect to these guys, this A is not a random matrix anymore. It's a fixed. So, A is no more a random. You fixed a vector, Now, it is not that I fix a vector and my A is, I choose my A random. No. Because what does they say? You fix your anything X. I am going to choose my random A. Now, I am using both is fixed. My vector is fixed because whatever you have got, this is what you are going to apply. And now your A is fixed. But maybe for this particular, for this vector, some other A, if I choose randomly, that is good. But this A, maybe for him, these are the vectors where he is doing making a mistake. Right? And he precisely has given him this. So you will fail this with probability 0. So this is like dependent event on each other. So how are we going to avoid this? So how do we avoid this? What do you mean the same family?
One more, we just pick another A prime from.
Yes. So what does these guys do?
I don't understand. We are so to say A multiplied by this thing is not equals to 0. We are applying here union bound.
You are not, it's not, look, A is not random for these vectors.
But A is random for not that sum, but the each of
Once you, no, but I'm only interested with respect to these vectors, right? Like some of these guys. When I applied A to this, or another way of looking at this, is like, this is not very scientific reason, but here it is. Look, this guy only guarantees me that I will support an edge. This is what it guarantees you. I will support an edge. Right? Now when you did this vector, all you have, like you are in a bad choice, right? So basically what happens is that now all the edges which you had, which he supported, is part of inside the connected component. What it says? Look, I'm going to support an edge uniformly at random incident to me. Right? So when I am applying to him, for him it is any edge which is incident to him is uniformly at random. Right? So he chose this edge which is inside my connected component. Now what are you interested in? You are interested in uniformly at random over the edges which are going outside this connected component.
So the probability will decrease.
Yeah, it could decrease to 0. I don't know how to compute that probability. It could be just 0. You don't know, because how do you know how to compute this probability? So what you are saying, let's forget this index. Look, you are saying let's forget this index from this and see if there is something from, I have to forget this index, and then from the remaining guys I have to find if there is an index or not. There is no guarantee that it will give you.
That is not what I'm asking. I'm asking that for this vertex, what is the probability that the edge it chooses is the one that is going outside?
What, come again?
Bigger vertex there, vertex in here, and for this vertex, I want to ask that what is the probability that the edge it decides to support, that edge is going out, not inside.
But then how did he, then it depends on the first thing, right? Then how did he select? Then it would have been a different connected component, no? So connected components which you are getting is a choice what edges you selected in the first case. So these connected components are a statistic process. So you are getting something from here. So you cannot say that now, oh, what is the probability? No, then then why are you in this connected component? Why are you not some other connected component? If I delete this edge, I have absolutely no guarantee, like if I delete this index, I have absolutely no guarantee that there is another edge incident to this guy. Okay. So, I mean, if you think about it yourself, you will start to understand the difficulties. So, what we are going to do, we are not going to have 1, but a1, a2, a log n, and I'm not going to send him one sketch. I'm going to apply him to, right? So, I'm going to give him a11, 1 2 tilde, a13 tilde, a1 log n tilde. 2 tilde dot. So, and this is what. So, and my central algorithm is supposed to use this vector in round 1, this vector in round 2, this vector in round log n. Okay? This is what he is going to use. Now, I have not used the property that it will support. It's still uniformly at random over all the edges which it can see. Right? Now I can apply whatever I was applying my analysis, but now this will increase by log q. Okay? So, this is my algorithm. Okay? Okay. Now we will make this algorithm in a streaming setting.
So what do you do if you fail, let's say in one round,
Huh?
you apply this A and it's high probability of them getting edge out of the component. But if you did not, it is going to
You will fail. You fail. Like graph, for example, graph was connected and you have reported the graph is not connected, right? But it means you have failed in some round, right? So you will sum this probability. But in each round you are failing with probability 1 over nc. Even after applying union bound at each, you are failing with probability 1 over nc. So like one other log n wouldn't matter. Okay. Okay. So now we have to make this algorithm in a streaming model. What I mean by streaming model? Edges are coming. So we already made an algorithm to maintain connectivity when edges were just inserted, but now edges could be deleted. Okay. So this is why we did all this hard work. But let's notice, first of all, how are we going to maintain this? And look, this A which I did here is too big an object that I can store. I mean, it's too big an object. I mean, log n, I mean, how am I look, here he took this, multiplied this and did everything, right? Now I do not have such liberty, okay? So now we are moving towards streaming algorithm, okay? So now we want streaming algorithm to maintain connectivity. And streaming means dynamic streaming. So what is happening is like, so you have an operation which says EI add, or you have an operation EJ delete. Okay, so this is what tells me that edge is added or edge. So this is what tuple it is. Okay. First of all, let's see if we do not care about bits and bats or all this kind of thing, how will we maintain this? Okay, like, so notice one thing. Look at your matrix A and X. What is this? So suppose this is a column A1, A2, or let's say matrix B, because we are already overloading A, B1, B2, B log n, for example, or BL. Okay, so the best way to view this is nothing but what is the first entry? It is B1 dot product X. What is the second entry? It's B2 dot product X, and last entry is BL dot product X. Right? It's a dot product. Okay. So suppose for now, okay, okay, I'm storing for every vertex, I'm going to store log n matrices. Like, I'm just going to implement this, but slightly more streaming version. Okay. So what I have at this point of time, imagine that I have somehow an access to, like, I have a global access to say A1, okay, A2, A log n, okay. But my here the data structure which maintains cannot see this. He can only ask, give me a column from A1. So I will give you the column from this. This is what you can ask me. What can you query me? You will not see these AIs. You are not allowed to see this AI. But you can ask me, query me from each AI. So what is the query which I allow you? And we will make this query later out of this. So the query allowed is, give me ith column of AJ. So this is the only query which you are allowed to, right? So these are the matrices with these properties, like it is known, and I will be truthful. If whenever you ask me this, I will give you the column of this. Okay, I will give you a column of this. Okay. Now with this query, I would like to maintain everything in n polylog space, and later we will see how to get this query in polylog space. Okay, is the question clear? Right? So in the beginning, what I'm going to maintain, for every guy I have data structure. Okay, at least in some lecture of my life I'm using the word data structure, so it is fine. Okay. So for I know number of vertices. Okay, so I have V1, V2, Vn, and what I'm going to maintain is, rather write, no, let's not write V1, V2, 1, 2, n. So I have n data structures. and each data structure has how many objects? This is a vector which I'm trying to maintain. Okay, so it is a current A11 tilde A log n tilde. This is the current one. At the current, in the beginning I have set this to 0. In the beginning all these data structures is set to 0. Okay, here I will have A11 tilde A n log n tilde. Okay, I have kept this data in the beginning. Huh? These AIs, because this is like a vector, row vector of size log n, right? Log square n. What is this A11? Right? When you multiply with AI, so it's a vector, a small vector.
So AI is 0. That's why it is.
Yeah, so in the beginning nothing has come.
AI, the huge H2 vector is all zeros.
Yeah, because nothing has come.
Right.
So in the beginning graph is empty, so I have initiated what do you call it? Yeah, okay, whatever, instantiated with all zeros, okay, in the beginning. So all these guys are 0. Now suppose an edge comes, what will we do? What should we be doing? Now we don't need this because we know what we have to do and we have to just get rid of these queries. So edge has come. Suppose I have come ij add. What should I do? Suppose this is a query, it has come. I would like to maintain that this is the correct set of sketches for the current set of graph. What should I do now? First of all, I must know that looking at ij, I know
Which entry in that
big matrix, right? Big matrix. This is a column ij, right? In the big matrix, what is this columns are indexed with? Columns are indexed with the edge number. So I go to ij number. Look at this. This is a column. I ask him. I ask A1, give me ijth column. Gives me ijth column. I ask A2, give me I comma jth column, whatever that means. So it all returned me these columns. Right? Now if you think this edge was not there, no? So all these entries are 0. Is it 0? No. No. It is not 0. This is A1 matrix, for example. For example, the others will be the same thing, okay? So this is not a 0 matrix, okay? This will be like 1, maybe 0 here, maybe something, then some 1, 0, maybe some Ri, and all those kind of things will be there, right? It's like some log square n size object, 3 log square.
So, just one question. We do not anyway have to store this A1 to A log n, right? Because when we want it, we can just generate it by creating a probe. Because we know I and j, we know that we can just create the random column at that point of time by doing probability of 1 by 2 power I or not. At that point of time, we can just generate this column and then multiply it with I comma j, instead of storing this separate, which would create a lot of space.
We'll get there. Why? Think about it. Why? Second time when you generate, yeah, it would have been great. Yeah, I do this, but the matrices which you can get is different. But I want the same matrix, otherwise I cannot apply linearity. So I cannot apply this trick.
random but fixed.
But fixed. Once I have taken this, it should be fixed. Otherwise, I cannot apply my linearity to, right? So you cannot generate on fly. Okay? So we'll deal with it. Okay? I just want to tell you why we cannot do this simple thing, right? But for now, let's just do the simple thing, and then we will do the heavy lifting. This is easy. So you gave me this, and I can like this query, so I can get this.
Our dimension of A1 was log n cross n.
No, it was 3 log square n times n choose 2. Because now we are talking, but like n is like n choose 2 vector, right? So this is n choose 2. So n choose 2. This is what we are. Right? So, yeah, this is exactly what it is. Correct. Okay. But now, if I did this and I did this guy is only going to multiply with this entry, right? And going to add to this sum, right? So what should I do? It's basically, I look at this and I can actually do nothing because it's 1, right? So just take this guy and add it to your current vectors. That's it. So this is what I will do to I, which is smaller. But what should I do to the j? I should take minus of this and add. Because look, here I have either 1 or minus 1 based on whether I is less than j or j is more than I, right? So if I is less than j, then at ith place I add minus. No, then I add 1, and at jth place I have to go and add minus 1. Like, so think of this. So you basically you want to multiply this guy with a big n choose 2 vector where at this I comma jth entry either you have plus 1 or minus 1 depending on which guys you are trying to do. So basically you are multiplying this with this. So it's like this into this, this into this, this into this, this into this. I can also think of this way. Look at this map. If I knew this ax, what is this? Ax plus a times this big vector. What is the big vector? It is 0 everywhere, but at some place I have put plus 1. And what is that place? I jth entry. This is what is the sketch for a I 1 tilde will be. And what will be the sketch of a j 1 tilde? I have to not plus 1 but minus 1. You look very confused.
What is little ai?
Little ai's are the sketched object. Is like little ai's.
Not tilde.
Hmm?
Not tilde. Asking about little ai.
N choose 2 vector.
Oh, ai is n choose to it. Okay, fine.
N choose, right? So whose projection is ai?
Okay. Okay, it's not the row of the.
No.
Okay. Okay.
AI, right? So I'm saying this is why. So if I have to multiply, right? So I take ax, which is I already have stored, and I take a and I take a big vector, which is just an incidence vector for this edge, right? Which if I is less than j, then I will put plus 1. If for the jth guy, I will put minus 1 and then add it, which is basically I look at this column, and if it is plus 1, I take this number and I just add to current. It is like ai1 tilde plus this vector, and for a ji1 tilde plus this into minus 1. That's it. So this is how I can update my information, right? And this I can do it in log n, order log n time update. Okay. The reason why I'm using the word order log n time update, because this is how dynamic algorithms have actually made this. So it is important not only that we can do this, because here time is not important, the space is important, but actually you can do this update in Polylog n time. Okay, good. So this is possible. And if edges delete,
Column size is
Polylog n, yes. Now suppose I delete. Suppose you told me.
No, it doesn't. Because there are only 2 entries which are changing this from what you had.
Yeah.
There are exactly 2 entries which have become less than minus.
And if you delete, you have to do the same thing, but plus 1 somewhere, plus 1 to the higher guy, minus 1 to the other guy. So you can do this operation. There's nothing stopping you. So, and I can ask for give me column of A1, A2, A3, and I do this with everybody else. Right? So in terms of space, I'm never using more than n polylog in space. Right? Given that I can implement my query correctly. Okay? So now let me implement this query correctly in next 25 to 30 minutes.
Which query?
Like this column query. Right? I didn't tell you, like this is like a column query. This is like some oracle. I want to make this oracle now an algorithm. Okay?
Without randomness.
No, there will be a randomness, but randomness will be on top, not the way Niranka was telling that let's generate on the fly. We will know this guy, and so it will always generate the same set of things. Okay? Okay, good. So all is well. All we need to do is how to implement this oracle. Okay, so we will spend our next half an hour to do this oracle, and if we are lucky and we are able to do fast, then I will give you some more applications of this. Like next couple of lecture is about applications of this to finding minimum spanning tree exactly, finding minimum weight spanning tree, bipartiteness, case connectivity, what is that called? Sparsifiers, everything. Okay. You have just seen L0 sampling. You have not even seen LP sampling. So this is exactly what is called L0 sampling. So actually, we could say something more here, that you do this with probability 1 over support. So like it's uniform over its support. Like this is it, and that is also used in some applications. So when we get there, we'll get there. Okay. So now we are going to if you recall the proof, when we were showing the proof, so probability that my index set intersection S for some S is equal to 1 for some S. Remember this. Let's just go through this proof for a minute, because there hides the key what should we be doing here. Okay? And this is the reason why I did not tell you the proof before. So what did we do? If you recall correctly, we said, hey, look at your index I. This index I is between, say, some 2 to the power I minus 2 and 2 to the power I minus 1, some number. Then what did we say? We said probability that I intersection S is equal to 1 is same as summation, okay? Some guy belongs and some guy doesn't belong, right? J in I, okay? Probability J belongs to Si, okay? K does not belong to Si for K not in K in A minus J. This is what we wrote, right? Look, what is I intersection S equal to 1? It is sum over an index, look, J belongs and other guy in I does not belong, sorry. Other guy in I does not belong to it. This is exactly what it is. And because before we were doing, oh, each entry in ith row will be probability 1 over 2i. So what was it? If we did summation ji 1 over 2 to the power I, right? 1 over 2 to the power I times 1 minus 1 by 2 to the power I mod I minus 1. This is what we did, and we did all this computation to show this is some 1 over constant. But this is what our whole idea was. This was a simple proof, right? This is exactly what it is, because everything was uniformly at random, right? So I can write this into this. But this requires full independence. If I think of each column being a random, like what do you call random variable, then it takes 0 or 1, like each xi's are basically independent random variable. No one depends, because for everybody I just go flip a coin, and if it with bias 1 over 2i, I put 1 or 0. So it required full independence, otherwise I cannot write this, right? So now what we will show that we can implement this whole idea with two wise independence. Okay. Okay. So let us implement this with hash function. Let us implement AIs with hash functions. Okay. And this is cool. At least it blew my mind, so I hope it does yours too. Okay. We say a collection H of functions D to R, like some domain to some range, is k wise independent, if for any set of k distinct values x1, x2, xk, okay, in D, and k values j1, jk in R, okay, and this is important. When we pick, okay, H uniformly at random from H, then what happens? Probability that H x1 equal to I1, H x2 equal to I2, so on and so forth, H xk equal to, sorry, what to write? J1, J2, Jk is equal to 1 over R to the power k. This is the property of k-wise hash function, right? So if I pick from H uniformly at random a hash function, it has this property that said this. And one example of hash function, we don't need this. One family of hash functions, k-wise hash functions, is A0, okay, mod some prime, and Aj belongs to 0 to p minus 1. Okay, so it is a family of hash functions from n to 0 to p minus 1. So basically you evaluated this. This is 1, and p is a prime greater than n. What does this implies? If I am looking for two wise hash functions, what is the family of H? What is the size of H? If I am looking for two wise hash function,
What is the size of range
yeah,
for k-wise?
for example k wise,
Whatever you written down there, what is its size?
what is its size?
We choose, we minus one choose. All we have to do is select
The-
those.
Yeah.
Yeah, it's not selection, it could repeat also, no? They don't have to be distinct. So it's like roughly p power k, right? And p is like some prime greater than n, and you always have prime between n and 2n, so it's like n power k, at most n power k, right? So for k equal to, it's polynomial many. It's like some roughly n square. Okay, good. So, and to store this H, how many bits do you need? So if I have a k by hash function, one hash function, how many bits of information do I need? It is completely quantified by this guys, right, and p. So it's like k log n bits, right, or roughly order k log p bits are enough to store k by hash function, to store all k by hash function. Okay. So what we do now, so now I need to define this matrix A, which is same as defining S0, S1, S2, S log n, right? The indexes where it is 1 and 0 otherwise, right? Log n if you really like. So what we do, let H be uniformly at random chosen 2 by hash function. I chose, done, dusted. Right? So I chose H in the beginning. And now I'm going to find everything according to that. Okay. So what is Si? What is Si? It is x in 1 to n such that h of x is divisible by 2 power I. Two power I. So all those indexes for which if I look at h of x, that number is divisible by 2 power I. So that is my Si. Okay. So I have told you now how to construct this. So if all is well, if this Si also has the same property as before, then our oracle is done, right? Then our oracle is done because I have fixed my h, I know, so I know my p, okay, log n bits. I know my h, bits 2 wise independent, some another order log n bits, okay. You gave me an index, you give me your index, right, ij. I evaluate hij, right, I evaluate hij and see, is it divisible by 2 power 0? Yes, then I put 1. Is it divisible by 2 power 1? If it is not, then I put 0. If is it divisible by 2 power 2? Yes, then 1. And this is the way I can get my vector. So if this is correct, I have taken care of my oracle, right? For A1, I will use one hash function. For A2, I will use another hash function. A log n, I will use another hash function. So order log square n bit. Agreed? So if I know my h, right, and this is how I'm going to construct Si, then if you give me an index, I can generate that column by computing this value h of x and looking at which all 2 y's 2 to the power I divides it. If it divides, I put 1, otherwise put 0. I have got my column, right? And once I have got first column, second column was what? Write down the column number. So please write down the column number. What was the third? But we also had a random number to r to the power I. So you also store that random number beginning itself, right? Then you take r to the power I. So you, because look, to construct our A, we had this, then r to the power I. So that r is some random number, right? So you also keep another random number beginning itself, some r in some big range, right? For each of these guys. Some polynomial, yeah, polynomial. So you keep all this, now you keep applying this, so you can actually get everything. So if I prove this, then I'm, yeah, if I prove very similar statement about SIs, then I'm done. Agreed? Yes. Question? So I'm going to replace my oracle with this machinery. Okay. Excellent. Okay, all is well. Okay, now I can drop this, you all understand this. I will not be doing for other examples things in so much gory detail. So I have made my hands dirty once. You all should make also your hands dirty once. Otherwise, it will be trouble. Okay. So let's ask this very simple question. What is the probability that J belongs to Si? Let's see. How many of you know has functions? Let's call this gamma I. What is the probability that J belongs to Si? What is the property of H?
So H of J is going to behave randomly, take you to
Yes.
anything in between 0 to -1.
Completely uniformly at random.
So you need to know how many numbers are the same.
That's it, which is given by p minus 1 2 to the power 2 power I plus 1 divided by p. This is it.
These are the numbers.
Now you can ask why, because as Venkatesh says, H is uniformly at random over 0 to p minus 1. Do you see this? If H is 2 wise independent, do you see this is true? No? Let's fix x1. And if you do not know this property, then you will have a hard time using ever has functions in life. Okay. Suppose and you fix j1. What should I show? H of probability that h of x1 is equal to j1 is equal to 1 over p. This is what I need to show. Okay. Which is same as you fix some other x2. Some other x2. Okay. Probability that j in 0 to 1 to p minus 1, probability h of x1 equal to j1, h of x2 equal to j. Agree? This is exactly what it is, right? If x1 takes j1, x2 will be taking something, right? But what is this? 2 wise independent, right? So what is this? 1 over p square, right? This number is 1 over p square because 2 wise independent function has 1 by r to the power k, ky. So 1 over p square, which is same as p times p square, which is 1 over p. So what I have shown to you that this is actually not one, like it is at every index it is uniformly at random, every subset it behaves uniformly at random. It's like a linear independence. If the k things are linear independent, so it's subset, right? And that is why I wrote what I wrote. Okay. So for sufficiently large p, I'm doing some approximation, but okay, this is approximately equal to 1 over 2 power I. I'm just going to approximate it just for like for large p, this is exactly like 1 over 2 power I. Okay. Okay. So I have this and I want to do this probability computation. I like now that I have shown to you, I would like to do the probability computation given that what is a I, like this is what I will choose I between this and this, and I have to show you SI. So look, there is some SI I have chosen for you, right? I say that probability that I intersection SI is equal to, so given how many indexes you had, I have a choice to choose will be great for you. So I have chosen which SI is great for you. Okay, now let me write down the proof. And if we succeed this with constant probability, we are done. So first one, there is no difference. This is exactly what it is. Right? So now I'm just going to do, so basically think of this as it's an AND of K events, right? J belongs to SI and K does not belong to SI for AND. So this is AND. So I can write down this summation J over I, probability probability K does not belong to SI for K in I minus J, okay, given J belongs to SI times probability J belongs to SI. Agreed? Just a conditional probability. Okay, so summation J belongs to I and probability that J belongs to SI I have written as gamma I. So let's write down this gamma I. Okay. So let's look at this space of the world. Okay. So what is an output of this random experiment? It's like some subset of indexes, right? Think of it, some subset of indexes, and I can identify those subset of indexes by putting 1 or 0 at 1 to n, right? So of this random process, what are the possible outcomes? So possible outcomes, I can map it to 2 power n, which is like 0, 1 vector to the power capital N, and I put 1 if that guy belongs to SI. That particular index is 1, then I put 1 or 0. Okay. Now, what is the good object here? The good object here, which we are looking for, is some subset here. And what is the property of this? For every index I here, look at this. Every index I here, look at the jth guy, it is 1, and for every other index it is 0, 0, 0. This is what it is. Right? What are the good what are the SIs I am considering here? Here. Right? J belongs to SI. Like J is some index which belongs to SI. So suppose this is 1 to n, and here it is J. It is 1, belongs to, and none of the other guy of my index belongs. So all those places I want 0 vectors, right? So this is basically my good event. So what is an outside event? It is those SIs, or it is those 0 to the power 1 such that at least one person contains at least at one index, you definitely have some element of I. It belongs. Okay, which is same as, so look at what is this set? What is this set? What is the property of any set here? It clearly, there exists some J, some say K in SI for which there is 1. Otherwise, why is complement? Why it is in the complement of this guy? Because at least for some K in my index, it belongs to this. Like it belongs. This is what it is. All these things are. So I can write down this as summation J in I, gamma I, 1 minus. You will see probability K belongs to SI, right? Summation over K in A minus J, probability K belongs to SI given J belongs to SI, right? This is what it is. Because I have taken union bound, so I am only subtracting more because maybe two sets could intersect, right? So I am only subtracting more, I am not subtracting less. That's all. Okay, so what is outside? Outside are those vectors which for some index in I contains 1, which is not j, right? These are the only bad people. And what I'm saying here, hey, let's write down all k in Si. So of course, the moment I put k in Si, I go outside, but I don't care about other people. So maybe this will be counted twice. Also, the vector where somewhere else this is 1, I don't care, because so some vectors probability mass will be computed. This is just a union bound here. Okay. Okay. What is this probability? What is this probability? Apply two-wise independence, no? So this is same as saying probability k belongs to Si. Because I can write probability A by B is probability A intersection B divided by probability B, right? And this will get cancelled because probability A times probability B because of two-wise independence. So basically I will get this. This is here the only place where I'm going to use it is two-wise independent. Otherwise, what is the point of using two-wise independence? Right? I would have just used one-wise independence. So this I can write from here to here. This is actually equality. There's nothing from here to here. This is equality because of two-wise independence. Okay. Now, I want to subtract. Look, I want to give a lower bound, so I want to subtract more. So I know, I don't know why I write A, because all these are I, sorry, it's my mess. Yeah. What is the size of I? Upper bounded by 2 power I minus 1. And what is this probability? Roughly 2 power I. So what is this probability? Half. Right? So this is equal to half comes out, and j in I, gamma I. Okay, but what is I? Did I use 2 power I minus 2 somewhere? Is it correct? No, I should use 2 power I minus 2 here. No? Shouldn't I use 2 power I minus 2 here? Or this is correct? Because you are subtracting more, right? So this is okay. But here I should use, no, this is fine. This is okay?
Should there be a one-time p squared here only?
Why?
We are taking k belongs to Si when j belongs. Yeah, but we are using the two ways. We have to also use the hash family.
That is inbuilt here. It is inbuilt here. That is a property that otherwise I would not have used that property. That is where exactly you use this. Okay, so let's just not mess up much. What is the upper bound on this size? Right, okay, I always get confused. 1 minus x is greater than or equal to 1 minus y. It implies y should be greater than or equal to x, right? Yeah, then this is correct, no? Yeah, because you want to maximize this, then you maximize this. Fine. So, what do we get? This we get half and summation j into I gamma I. So, what is this? 1 over 2 power I minus 1. So, I is at least this much, right?
So here we have to use the lower.
Here it is.
Here we have to
Use lower one. Sorry. So, you will get roughly 1/8, no? Which is fine. Right? So I have shown to you that it just happens. Okay. I have used some approximation here, but that's it. So there you will get some error term, like little bit of here and there, but this is it. So this is the whole algorithm, right? So what did we learn? We can implement L0 sampling using 2-by-hash function. This is that I taught you. If I can implement L0 sampling using 2-by-hash functions, then we can do connectivity in streaming model in n polylog space. Okay. So dynamic graph algorithm, they don't care about space, they care about two things, update time and the query time. They do not care about space, they care about update time and the query time. What is an update time here? Polylog.
So where is the n polylog in space?
Because Venkatesh, for every vertex you are storing these vectors, right? That is where, right? AI tildes, right? So you are keeping n log in AI tildes, and each has some polylog in dimension. And as he says, maybe the bits also. So if you really count bits and everything, it will be n power polylog. It's a big C, okay? But if I just use dynamic graph algorithm, I could have just used this thing. Update time is great for me, polylog, right? Whatever I'm storing, I can update in polylog time. What is not good? If you ask me whether this graph is connected or not, what I have to do? I have to apply this Borovka's algorithm, and it can take linear time. Right? So query time is not good, but update time is great. Okay? So after this paper, people came up with this dynamic data structure to maintain connectivity. This is so basically it is this algorithm. On top of that, you apply you do some data structure which I do not know to test, like to tell you connectivity immediately. Okay? So I hope I have conveyed something interesting today to all of you. At least I found it very exciting. I mean,